Hello everybody. The goal today, as Lior mentioned, is to discuss the problem of estimating the triple product of Maass forms. Now, the majority of the lecture is actually going to be devoted to better explaining the concept of Maass forms and see various motivations to be even interested in this problem and appreciate its significance. So let's start in a very broad context. So let X be a Riemannian manifold. So there is a very general concept of a Laplace operator that operates on infinity functions on X. In this generality, it is given as follows. The Laplacian is given by minus star d star d. Okay, so let's study this definition. The first operator d takes a function into one form. The star takes it, the Hodge star takes it into an n-1 form. Performing d once more takes it to a top degree form, and performing the star returns us to the zero form realm in which we wish to be. So this abstract definition really does give us an operator on the ring of infinitely differentiable functions. And one readily sees that it is a differential operator of degree 2. So one can try to compute this operator for concrete examples. So for example, if we let X be Rm, this becomes, I believe, the minus usual Laplacian. Okay, and we know that, and we are all familiar with the definition that those functions for which this operator vanishes are the harmonic functions. We are actually interested in a different setting, namely X being the hyperbolic plane. Of course, this definition can be computed explicitly for arbitrary dimension, but we are only interested in dimension 2. So this Riemannian manifold I defined here has a concrete model. It is the upper half plane with the hyperbolic metric. In this case, it is easy to compute that the Laplacian is actually y squared times the Euclidean Laplacian. And one can ask, well, we obtained an operator on this space, say infinity of X. We can try to study its spectral behavior, namely see whether it exists as an extension to L2 and study the spectral behavior of this operator. Namely, one can ask what kind of good spectral behaviors it possesses. Is it bounded, compact? All sorts of questions like that. Well, the answer is that while differential operators are seldom well-behaved, integral operators are well-behaved. And we can say the following thing. So suppose X is now a compact Riemann surface. Then it's L2 decomposes as a discrete direct sum over the eigenvalues of the Laplacian. And the Laplacian is self-adjoint, and the eigenvalues are positive. Of course, we have 0 because the constant function, its Laplacian vanishes. Okay. So this gives rise to the following natural definition. A C-infinity function from X to R is a Maass form if it is an eigenvalue for the Laplacian. Okay, so there are a few remarks in order. A, why did we impose the compactness condition? It seems a bit off. Well, the end of the assumption that X is compact but then in order to obtain a useful concept, one has to control the behavior at the cusps. What do we mean by that? Well, since where X bar is compact, so we are interested in functions on X, but we can ask, well, yeah, suppose X is open dense in X bar, the complement is a finite set of points. One can ask, do we have poles, so to speak? I mean, we're dealing with C-infinity functions, but do we have something that is analogous to a pole in those singularities, or do we have something worse? So in order to obtain a concept that's useful, one has to impose a growth condition at the cusps, namely at the complement of X in its compactification. So that's one remark. Now, the second question, another very natural thing one can ask.
Can I ask a question?
Now, suppose, yeah, is there a question?
Yeah, why is if X is not compact, why do you assume there are cusps? Can it just be an infinite area or something?
Excuse me? Well, we're going to specialize to a hyperbolic setting, but
yeah, it's a very special situation. The general manifold, you have no chance of saying anything, even in finite volume. So
I'm sorry, Zev, I can't hear you properly.
I'm saying that it's a very special situation for a general non-compact but finite volume manifold. There is no chance of saying anything because there will usually not be discrete spectrum. So you may as well just assume that you have a hyperbolic manifold or something like this.
Yes, that is the next remark, that our theory only works well. We are indeed going to specialize to the case that X is hyperbolic, namely its universal cover is H. Okay, so now I want to turn the tables all together and see, well, this concept obviously arises in many different settings that are of interest to different people. But for me, the motivation to study these objects is their intimate relationship with representation theory of reductive groups. So now we're going to take a wide detour and study representations of PGL2 of R. Now, PGL2 of R, well, we choose this particular group for technical reasons that it's going to be hopefully clear at some point. But thus far, let's just think about this theory. So let G be PGL2 of R. And we want to consider representations of G at the moment, continuous representations in a Hilbert space. So V is a Hilbert space. And we consider homomorphisms from G to GLV, where GLV is a space of bounded operators whose inverse exists and is bounded. And we want to impose the condition that the evaluation mapping is continuous. So in this setting, one can ask, well, how do these objects behave? Well, the simple-minded answer is that they are very difficult objects to deal with. They are very large. So one wishes to focus on a subspace of V, which is going to be significantly smaller, but still encapsulates all the important information in the cases we are most interested with. So, so first we have to impose a condition about V to make sure it's not too large. So we let K in G be a maximal compact subgroup. Okay, so it's going to be a one parameter subgroup parameterized by an angle. Okay, and we want to impose the condition that for every irreducible representation, sigma of K, if I take it at the number of copies of sigma appearing in pi, I want this number to be finite. So this condition is called admissibility. Now, let's think a little bit about this notion. What am I aiming to achieve? I want to have all finite dimensional representations in my class, and I want to have all irreducible unitary representations. It's not immediately obvious that an irreducible unitary representation is admissible, but it is true. And this is, at least ideologically, the minimal class of representations which contain these important examples. Okay, so so with this condition out of the way, I'm ready to make the first important definition. So let X be an element of the Lie algebra. And I want to try to define an action of X on a vector V. So how will I do that? I will try to define an element as follows. Okay, so this limit may or may not exist. Usually it will not. For a generic element in any reasonable sense, it will not. But this attempt gives rise to the following definition: a vector v in v is infinity if this iteration of this limit is defined for all elements of the Lie algebra. So if I'm only interested in those C infinity elements, then I obtain a representation of the Lie algebra. Well, one might ask, are there even such elements? Are there many of those? Well, it turns out that C infinity is dense. Well, that's in Grizz's notation. It is usually denoted by V infinity. This is a property of admissible representations. Now, this is not quite good enough. V infinity is still a bit too large. So we are going to make a final definition. A vector V in V is K finite if the subspace, the algebraic span, is finite dimension. Okay, one might ponder at the relationship between the two definitions we just made, and it's a pretty easy computation to see that Vk is defined to be all the K finite ones lies inside V infinity. So let's see what good properties Vk has. So it's clear that Vk is K invariant. One can check that Vk is G invariant. And lastly, Vk, I claim, is a countable algebraic direct sum. Okay. And what is this n? So the parameter n runs over all the irreducible representations of K. Now, what can we say about those? Since K is compactly abelian, these are just characters of K. Characters of K. Is the same as integers. So this Vk has many good features, as we can see. It is a representation of K, a genuine representation. It is a genuine representation of Gothic G. And it is a pretty manageable algebraic object. Namely, it's an algebraic direct sum of finite dimensional vector space. Now, what is the one feature Vk does not have? Vk is not a representation of G. One has to come up with a name for such things. So a GK module is a vector space space V together with an action of G, action of K, they must be compatible. And we want them to be, we want this structure to be admissible, in a sense comparable to the one we had before. Okay, so given a representation in this very wide class of continuous representations in a Hilbert space, we managed to cook up a new thing, this VK, the Harish-Chandra module, which does seem to have nice algebraic properties, but one can ask, how much information did we lose doing this? Well, in an arbitrary case, we might have lost quite a bit. But we have the following important theorem. If we restrict this assignment to only unitary representations, unitary admissible representations, sorry, unitary. We want UG to act by unitary operators, then this is an equivalence of categories. Therefore, if we are only interested in unitary representations,
could I maybe just ask what are the morphisms on both sides? So can I take it back? So on the bottom, I understand, but on the top, I'm not sure.
Well, one has to define this notion. I mean, these are maps of vector spaces that are compatible with all the structure we put.
I'm talking about the unitary ones. Do the maps between the vector spaces somehow remember the Hilbert space structure, or are you completely forgetting it? This linear maps commuting with the actions.
They have to remember the structure.
But then if they preserve it, it's no longer a vector space and your categories are enriched over different things. This is what kind of confuses me.
By the way, who is asking? I cannot see.
Stefan, sorry.
Ah, hi, Stefan.
Hi.
Yeah, one has to take careful care with the functional analysis in order to describe this equivalence of categories. But I actually am only interested in the simple objects.
Okay,
so that's going to be particularly easy. The one takeaway I want to have from this diagram is that if I'm only interested in classifying unitary irreducible representations of G, all I have to do is to study simple GK modules.
Okay, cool. Yeah, thanks.
Okay, so let's ponder a bit now about what a GK module looks like. So I already told you, this was an obvious observation, that VK as a K module decomposes a direct sum Now, one can ask, does the existence of a G structure in any way limit the possibilities of En? Does the irreducibility in any way inhibit the features of En? And the answer is very much positive, but I won't dwell into the entire classification because I want to specialize into a very specific type of representations, which is k modules. Okay, I have multiplicity 1 in each odd degree. Where I remind you how we define Vn. So we said it in slightly abstract fashion, but what this really means that the action of that V is given by the scalar okay, namely this group K acts by this particular character. Okay, so so one can ask, once I set this particular isomorphism type as a representation of K, how much choice do I have as to the structure of a UG module? Well, if you study this carefully enough, this depends on a character of the Borel. And once you compute all the various compatibilities, this G structure really boils down, this G structure on this particular isomorphism type really boils down to a complex parameter mu. Okay, and this gives rise to the following definition. Okay, just another point, I'm sorry. What we did not address at all is the question of whether this representation is at all unitary. Okay, we said that when we move from unitary to GK module, we lose nothing, but we did not say under what circumstances a GK module is at all a unitary representation. And this question is not always easy to answer. And it turns out that in this case, the answer is the following. If mu is imaginary.
Asaf, is it like representability or something like this, or similar idea? So you want to know which modules come from unitary, so which one are representable by unitary, or maybe not representable. Okay, so I got confused. I answer myself.
Well, I'm not really versed into this subject. Well, let me write the answer and ponder about it. So if mu is purely imaginary, it's actually fairly easy to endow Vk with a unitary structure. And I will describe how to do it in a second once we have a more concrete description of these representations. And for completeness sake, it's worth noting that if mu is real and of absolute value less than 1, then Vk is also unitary. This case is known as the principal series. In this case is known as the complementary series. So from now on, we only care about the principal series. The complementary series, I actually don't know by heart the formula for its unitary inner product. And in fact, in many senses, it is somewhat mysterious. And experts, as far as I understand, believe that it's sort of unitary by accident. Okay, so it doesn't fit into the picture as neatly. Okay, but let's now think about the principal series. So what I claim is that if I pick up U in IR, all we did here really is to consider functions from the punctured plane. We want a complex representation here with a certain homogeneity condition. If one unravels the definition, this is what we wind up with. And things being as kind as they are, it turns out that the most naive inner product one can think of, just integrating it over S1, this product, actually gives us an inner product. And the point is that the integrand is the real part of its homogeneous degree is -2, which really guarantees that this particular normalization, choosing S1, does not affect the final outcome. The other case, I really can't explain you any further, and we won't need it, because now we are almost ready to return to Maass forms. Let's take a step back and suppose V is a UG module. Where I should, I guess, remind everybody that UG here is the universal enveloping algebra. So suppose I have a UG module V, and let's think about how the center of the algebra acts on V. Well, it acts by UG homomorphisms. So this in particular means that if V is simple, an element of the center acts as a scalar. And furthermore, it is true that a simple VK module is a simple UG module. So now we are ready to the main observation here, that if we take a central element it's going to act by a scalar sorry, correct my okay. It's going to act by a scalar when it's where it's defined. Okay, now note the cunning notation I chose. I denoted the arbitrary central element by delta, which was my notation for the Laplacian. Now, this is of course intentional because we have a concrete example for such a central element. If we let R denote they generate the Lie algebra G. Then it turns out, it's easy to check, that if we define delta to be -1/4, then it actually belongs to the center. It follows the delta acts by a scalar on smooth vectors in V. Okay. Now note that this already reminds us of a Maass form, because this delta is clearly a differential operator of degree 2, but it's not quite that. Why is that? Well, for two reasons. First of all, we got a whole stock of elements on which the quote-unquote Laplacian acts by scaling. In the original setting, we were interested in only one, or a linear span thereof. And the second point is that these are not functions. These are still vectors in some obscure space. So in order to meld these points of view together, we have to introduce automorphic representations. Yeah, so far we were dealing with abstract representations. Now we're going to turn our attention to automorphic ones. So we let gamma in G be a lattice. Namely, we want this to be of finite volume. Two, G acts by right translation, so this thing is a Hilbert space representation of G. Now, for our purposes, an automorphic representation is an irreducible Hilbert space, unitary. Of G together with an embedding nu into this L2. Okay, so now no longer are the elements of V obscure elements in some abstract vector space, but they are concrete functions on G. Now, we're beginning to approach what we wanted, because while we don't quite have functions on H, we have functions on G. But they're, of course, as we all know, related. Observation. G acts on H with the stabilizer of I in H being K. Okay, if we chosen any other point, it would still be a maximal compound, of course. So now what are functions in H? They're just functions on G, which are K invariant. Now let's see if we have a K invariant vector in our representation. Well, we do. The action of K is determined by this expression, and in this direct sum, we have a one-dimensional space of k-invariant vectors, the ones corresponding the V0. Okay, so this very abstract representation, once we chose an automorphic model for it, exhibits some element in it as a Maass form. So conclusion of this entire journey. If V is unitary in the principal series, phi is k-invariant, not 0, then if we transport phi to L2 of the G gamma, is a Maass form. Okay, so we managed to tie up together the slightly analytic and flavor theory we had of Maass forms with abstract representation theory. Okay, so in the final third of the lecture, I'm going to state the problem that's of our concern and say a few words about how we tend to approach it. So consider the following problem. Oh, let me first, let me first do an example. Okay, so previously we discussed Maass forms on compact spaces. Now it's slightly challenging to give explicit examples, but once we move to non-compact setting, which is of course of great interest as well. For example, if we let gamma be S of 2z, then it is a lattice, but the quotient is not compact. It has one cusp. The behavior in this cusp, while we wanted to have it most of whole, we can produce interesting examples of Maass forms on this space called Eisenstein series. So there are a few ways to write it. Let me use the following notation.
Asaf, Eisenstein series are not Maass forms. Maass forms is a specific name for discrete spectrum. Eisenstein series are not Maass forms.
I saw various names. I saw various.
I know the terminology. These are not Maass.
Yeah, forms. I mean, in your work and the work of Sarnak, this is how it appears. But there are various.
Also, in the work of Maass and the work of Selberg, Eisenstein series are not Maass forms.
Well, yeah, I see your point. I mean, we're not going to be interested in particular in Eisenstein series, but rather in forms corresponding to the discrete part of the spectrum. But the way I defined it, okay, which might be unorthodox, it is a Maass form. So and I do want to use it for the demonstration. As Zev suggests, you might well be advised not to call them Maass forms. Okay, so I wrote a very explicit function, which depends on a parameter s and takes a variable z. One can easily compute that for s with sufficiently large real part, this series converges and gives rise to a infinity function. And if I wrote this equation a bit more cleverly, it would be readily seen that I'm actually averaging over the action of gamma. So this thing is going to be gamma invariant, and it's also an eigenvalue of the Laplacian. Now, Zav's comment that this function belongs to the continuous part of the spectrum raises the question, is it defined for all s? And this is a very interesting question with very interesting answers. But let's return to the setting that's of our concern, namely Maass forms that correspond to the discrete part of the spectrum, or as one would strictly call them, just Maass forms. So suppose we have fixed two Maass forms of phi and phi prime, and we consider the assignment, I goes to lambda I. Recall that the eigenvalues are ordered. Over H mod gamma. Well, okay. This is a numerical quantity that one can ponder about its asymptotics. We have a sequence of numbers parameterized by I, and one can ask how it grows. In particular, in view of previous results, that we know the clustering features of these lambda i's. And there are also extrinsic reasons to be interested in this formula, namely that it's related to special values of L functions. So it turns out some expression G, explicit expression, now, I don't define explicitly any of those L functions, but they're important in profound invariance. And it turns out that this triple product gives us a relationship between values of these L functions. So now I'd like to take a few words just to talk about how Bernstein and Reznikov approached the question of saying meaningful things about the asymptotic of this sequence of numbers. So their key observation was the following. Consider three automorphic representations, V1, V2, V3, and consider the Helm space into the trivial representation. Now, this integral we considered over here gives us an example of an element in this space of functionals. For every three elements of this space, of these spaces, sorry, we could evaluate this integral and obtain an invariant functional into C. Now, one might wonder how big is this space? And the mildly surprising answer is that it's very small. Now, at this point, we reap some benefit from my choice to use PGL2 rather than SL2, because this kills a second linearly independent functional that might have existed in this space in the case of SL2. So this is a technical remark. So in particular, the main observation was that if I want to say something substantial about this functional, all I have to do is to construct another functional, which we denote by L mod. On this, and then study two things: the value of this L mod on our Maass forms, and second, to study the proportion between these two functionals. And here I made a bit of a notational mess, but I remind you that we have previously fixed. Here the notation is symmetric, but I'm actually interested in the case where these two elements are fixed and I plug in a third element. So this notation makes sense. And now I can ask the question, what does AI look like? So as it turns out, these two questions are both interesting. For the first one goes as follows: can we construct in arbitrary generality a functional L mod which is easy to compute and has good behavior? And the answer is a resounding yes. Not only can we define this functional, but in fact, it's very easy to give a precise answer to this question. Okay. And the answer to the second question is a bit more involved. What is known to be true, you're right, is the following results. This is a fairly straightforward computation carried out by Bernstein and Reznikov, but as I understand it, there has been pretty substantial progress since. And let me just illustrate the main open question.
Asaf, I remind you that you have 5 more minutes.
Yeah, I'm wrapping up. Yeah. So I'll just state a main area of research in this field. Try to bound these coefficients for lambda i's in short intervals. This has various variants, but one of those is the following. Okay, so this is, as I understand, still an open question. Okay, I'm finished.
Thank you very much. I should have waited one more minute, but I'm sorry to interrupt you. Okay, thank you so much. Are there any questions?
Yeah, can you maybe state the conjecture, the tight upper bound for this quantity?
Yes, so there are various statements. So, well,